Hi, today I want to talk about 21 past paper questions on implicit differentiation, related rates, and optimization. I want to share some math tricks and my thought processes for these questions to help you prepare for a derivative test in the IB junior year. So let's look at the first question. It is an HL paper 1. You can see that it requires implicit differentiation to solve question 1 to find an expression for dy over dx because you cannot really isolate y. And for the second one, we want to find the limit as x approaches 0. And here, for which y equals x, that means we can just substitute y with x and then simplify this whatever is in their derivative and to get a value. So let's do question 1. What I do is that I copy everything down but move all these terms with variables onto one side. So it's this whole thing equaling 0 here. And then let's just do implicit differentiation. Notice that the terms like these are the product of x and y to some power, so we need to apply product rule. And for the terms with y, we need to do implicit differentiation, where we first treat y just like a normal variable, so we move 4 down, so it's 4 times y to the power of 3, but also times dy over dx, because y is a function of x. And now we have this long expanded form, and we need to isolate dy dx, so we just move all the terms that doesn't have dy dx to another side and add up all the terms that is multiplied with dy dx inside here. So now we can just simply isolate dy dx by dividing the right side by the left side, and we get this big fraction. So now let's find the limit of this as x approaches 0, and we substitute y with x, and it's clear that we can combine these like terms. And to this step, you will notice that we can factor out -1 from the top, because the terms on the bottom just got their signs reversed, so compared to the top. So we can eventually write that the limit as x approaches 0 is just -1 for this case, because we just cancel out these two and have -1 left. Let's look at the second question. It's also paper 1. So this one is for related rates, and we need to extract some information from the question to help build an equation that will help us solve. So it's asking for the rate at which the water level is rising. So we care about dH dt. So h is the depth of the water, so we care about this. And it's given that the cone is inverted and the maximum height is 10 meters and the base radius is 5 meters. So we don't want to have a ton of variables when we're solving, so we can just write r as h over 2, because 10 over 2 is just 5, so we can just write the relationship like this. And another information is that the water is being pumped into the tank at a rate of 3 kilometers per minute. So that means dv dt, which is the rate of the volume increasing, equals 3. And that will help us set up another, a big and important equation to solve. So before that, we want to get the formula for the volume of the cone, so which is here, and it's in the data booklet. And we can substitute r with h over 2, and after combining the terms and stuff, and we will have this, as v. So now we have v as a function of h. And the most important thing in related rates is to help us set up a form of equation like this to help us solve. So what does that mean? So like dv dt, the rate of the volume increasing, equals dv dh times dh dt. Well, why? Because, well, you can cancel out dh and cancel out dh, and then you have the same thing. So why do we do this? It's because this thing is given, it's 3, and this thing, we can obtain it by taking the derivative of this, and h is already given, so h equals 4. So we can have this as a numerical value and this as a numerical value, and we will know what the question is asking for. We will find out what dh dt is. So dv dt equals 3, and then dv dh will equal to, well, let's move 3 down here, which is 3 pi times h to the power of 2 over 12 times dh dt, and substitute h equals 4 in here. And then let's just simplify this. We'll have 4 pi times dh over dt. So dh over dt, the final answer is just 3 over 4 pi meters per minute. And it's not a calculator question, so you can just write it as a fraction. That's how you do that's how you do related rates, and that is the key. So this one is a paper 2, and it's a combination of optimization and some stuff related to the second derivative. So we have a rectangular piece of cardboard with these dimensions, and it's to be made into an open box by cutting the squares of side length x centimeters from the corners. So we have like a box without a lid, and we can draw it here. So these are the cutout squares, like these 4. And so for the new box that we have without the lid, this width will be 24 minus 2x, and this length will be 36 minus 2x, and the height will just be x. And this will help us to write a formula to express the volume. And the first question asks us to find the volume in terms of x, so we just set up Vx as the product of these 3, and then you can just expand it and it will look like this. So the second question needs us to use the calculator. So it wants us to find the value of x to maximize the box volume. So let's just plot this. And then we'll have that by GDC, the volume is at maximum when x is approximately 4.71 centimeters. And just add a little graph to show how you got it, like what it's on your calculator. So that's like plotting Vx over x, and then the maximum is right here. You don't have to like make a detailed graph, but that is enough to show that the maximum is there and that's the value. So yeah, and also very important is that it's good to show that x cannot be more than 12 centimeters, because 24 minus 2 times 12 is 0. Like it just cannot be 12. Like x cannot be 12. So it ends here. So it's important to show this detail. Now we have something related to the second derivative. It wants us to verify that this value of x, 4.71 centimeters, is a maximum. So that means we take the first derivative and then we find the second derivative, like we find this, and then we want to show that a maximum is a concave down, okay? Like this is a concave down, so that means the second derivative is smaller than 0. There are two ways to do this. Like one is like a little more tedious, one is like a lot quicker. So I'll go over the first one, like the more tedious one, but it shows you more clearly of like how to think about the second derivative test. So you take the first derivative and take the derivative of this to get the second derivative. And so at the maximum, this thing, like the first derivative equals 0 because, well, if this is a function and there's a maximum, then like the slope of the tangent here is like 0, so that's why. And if you plot this in the GDC, then you will have x equals these two values. And, well, that's our value of interest. So now we want to show that this thing is smaller than 0. And we want to know when it is smaller than 0. So we will find that it is smaller than 0 when x is smaller than 10. Well, in these two values, only x1 is smaller than 10. So like here, it is a maximum value. Another way is quicker, like you just put something in your calculator, like you take the first derivative and take the second derivative, and you directly put 4.71 into the x value here, and you will find the second derivative as this negative value, and that is smaller than 0, which shows that it's a concave down at this point, so it is a maximum. Eventually, let's just complete the problem. It says that to calculate the maximum volume to 2 decimal places. So you just substitute 4.71 as x in there, and then you will get this as the answer using your GDC. So the second question is a paper 2, and it involves implicit differentiation in the first question, and in the second one, it involves some trick, but it's easy. So in the first one, we want to show, so like, well, let's copy down this original equation, and let's just take the derivative. So this is a product, so we want to do the product rule, and we have 2xy, so we differentiate x first, and then times y originally, and then plus y to the power of 2 times the derivative of this. And then using the data booklet, cosine y, well, the derivative is just minus sine y, but times a dy dx because of y as a function of x. And then the derivative of any constant is just 0. So now, same thing, just isolate dy dx. We can move this term without dy dx to the right side here, and then isolate dy dx, make it like multiplied with the sum of these terms involved with it, and then just negative 2xy over this thing, and that just equals to what the problem shows. It lets us to show. So like, ensure your final answer looks like this. That's really important, like double check before you move on. And now we want to find the coordinates of the point P on the curve where y equals pi over 2 in this interval. So we might need to like check some values and like to ensure x doesn't go out of this domain. So what we do is we just substitute y back into this original equation and find x. So, well, after doing that, you notice that cosine pi over 2 is just 0, so like this thing equals 2, and x to the power of 2 equals this. So x has 2 possible solutions, but we want only this domain, so like x can only be positive, and we just write out this coordinate eventually, yeah. So this paper 1 question is a bit more complicated in the wording and like setting up the derivatives equations for related rates. So it's also about a water tank in the shape of an inverted right circular cone. So this is like 90 degrees right here. And with a semi-vertical angle of 30 degrees. So semi-vertical angle, well, that means like if you cut it half like this and half vertically, you have this right triangle, and then this angle equals 30 degrees. And the height is the maximum height, which is like 10 meters. And the water goes in at the rate of this. So dv dt is given as 1/2. So h is the depth of the water and r is the radius at t minutes. So first, it wants us to show that the volume of the tank can be given by this formula. Here we don't have r in there, so we need to find a relationship between r and h and substitute r with something related to h. So r and h, they're related by this angle of 30 degrees. So that's the opposite and that's the adjacent. So we had tan 30 degrees equals r over h. And so r equals h times tan 30 degrees, which is h times 1/3. So now we write out the normal volume formula for a cone, and then we substitute r with this relationship with h, and we just simplify, and then we will get this, and that equals to what the problem gives us. So now this one is similar to what we did before. Like we're finding dh over dt when h equals 4. So it's given that dv dt is 0.5. So dv dt equals 0.5 equals like what we read before, dv times dh over dt. Same reason, just cross out this and then you have the same thing here and there. Yeah. The reason we do this is like we want to use those numerical values given in the question like this, and the values that we can found and substitute like this. Well, because h is given, h is 4, so like we want to use this and this, like make them numerical values, so we can move them around and get dh over dt as a numerical value. That's the thinking process of this. So let's just take the first derivative of this, the volume, and then substitute h equals 4 in there, and now we have this, and just move around the numbers and you will have, why is it approximately equivalent? Sorry, it should be equivalent to this, meters per minute. That is the answer. The third question might be a little challenging because of the wording and what it's meaning. So h is still 4. And then now we turn off the water supply and the water is leaking out. And this rate is proportional to square root of the depth of the water. So the rate of the water leaking out is also dv dt, but now it's just negative. And this sentence here, it means that dv dt equals to negative k times square root of h. So what I did here is that k is the constant that I inserted, a constant that will bridge these two values. So the water is leaking out, so this is a negative rate because volume is decreasing. However, the height is always positive, so we have to make a negative sign here. And let's insert h equals 4, so we have negative 2k. And now we can utilize this thing we have seen multiple times to help us solve for k. So negative 2k equals dv over dh, which is exactly what we did before, times the given dh dt, which is this negative 0.01. Now we just have the numerical values for this, and we just move around and combine and simplify. So we have negative 2k equaling this thing, and let's just move negative 2 the other side. Now we just have k equals this. So now just looking back at this original equation and in relevance to this, we can write k in there as a numerical value. So copy this down right here, and dh dt, leave it as it is. And then now we just substitute negative k right here and leave h as it is. So why? That's because it's asking for that, well, since dh dt is given as this, we want to find a differential equation satisfied by h. So that means we want to have this equaling to something related to h, maybe to the power of something. So now we don't want to substitute h with 4, and we don't want a numerical value in the end for dh over dt. We just want like a function, basically, like an expression of a function, but now it's just the rate of water level decreasing. So we need to isolate dh over dt, and we want to keep this on the other side. So now just move this term to the right side and simplify, and then you end up as dh dt as a differential equation satisfied by h, written in this form, meters per minute. So that's what the question means. This question is a very comprehensive one, and it takes up 12 marks, so it's quite important. It involves implicit differentiation for question 1, and for this one, it's about knowing that the tangent is horizontal. Well, that means just dy dx equals 0. And for the third one, the nature of the stationary points. So now for that, we need to take the second derivative to know whether it's like concave up, concave down, maximum or minimum. So let's first do implicit differentiation on the original equation. So it's an easier one comparing to the previous ones, and just remember, apply product rule for this, and for the other ones like involving y, remember to multiply dy over dx, and show that eventually you get this answer by isolating dy over dx. So now we want to find the coordinates of these 2 points when the dy over dx is 0. So when it equals 0, that means, so this equals 0, then that means y1 minus 2x equals 0, because 0 divided by something is 0. So now we know that y equals 2x for this condition. And we want to find the coordinates on this curve. So we need to substitute y equals 2x back in there and find the x values available for this condition, and use these x values to find the y values. So, but after substituting y equals 2x in there and just simplify, and we get two values for x. So either it's 2 or minus 2. So now we just find y1 and y2, and these are the two coordinates. Write them out in this bracket form. And now we want to determine the nature of these two stationary points. We already know that the first derivative equals 0, so we need to know what's the second derivative, how it's doing. So like we want to know whether it's positive or negative. So we need to take the derivative of this to obtain the second derivative. The easiest way is to use the quotient rule, I think, because, well, it looks messy initially, but you just, again, do the implicit differentiation and simplify, you will have this very elegant fraction. Now we want to test the 2 points, whether by substituting y and x will give us a positive or negative value. So let's first do 2, 4. Just substitute 2 and 4 in there, and then you will have a negative value. So that means it's concave down, so it's a maximum. So now let's do -2 and -4, and it's a positive value. It's 1/3, so it's concave up, so it's a minimum. You need to write out words like maximum and minimum. Like you cannot just write out this inequality and just go. So like it's important. So this question is a bit similar to question 6. It involves implicit differentiation and also finding the coordinates of the points that satisfy a certain condition. The points are on the original curve, just to keep in mind of that. Let's first take the derivative of this equation to find out dy over dx, following the same procedure I've said multiple times before, and then after isolating, you'll have this, and you set it equal to 0. So for this type of question, like when something equals 0, you will need to find like an expression for it so that you can solve for the coordinates. Yeah. And now for the derivative to equal to 0, then this top, the numerator must be 0. So you can write it as x plus y times x minus y equals 0. So either this equals 0 or that equals 0. So either y equals minus x or x equals y. So let's find the coordinates for each case. Just substitute y with the value of x it can represent, and find the value of x first, and then use this to find the value of y. So the first point has these coordinates, and the other point, following the same procedure, it will have these